Just a moment.
Okay, so let's resume. Okay, so we're happy to have Luca here. I'm not connected. So we're happy to have Luca here, who's going to talk about the EFT stringy viewpoint on large distances. Please go ahead, Luca.
Okay, thank you. Thank you very much, Mariana. And I would like to thank the organizers for the invitation and also apologize for not having been able eventually to come to Corfu. I'm really, really sorry about that. So anyway, so coming to my talk, it is based on this set of papers written in collaboration with these people. Can you see my pointer? Can you see? Yeah, okay. And in particular, I will focus on this most recent paper written with Stefano, Fernando, and Irene. So in these papers, we studied some aspects of the physics of strings and membranes appearing in four-dimensional effective field theories coming from string compactifications. And as a starting point observation, such objects are quite universally present in these models. In particular, they typically arise from higher dimensional branes wrapping some internal cycles. And if we focus on minimally supersymmetric models, so models preserving some minimal supersymmetry in four dimension, which are usually the most interesting ones from the phenomenological viewpoint, they are still allowed to be VPS. That means that they can be included in a manifestly supersymmetric way into a four-dimensional effective field theory. In particular, strings naturally coupled to linear multiplets, while membranes coupled to appropriately defined free-form multiplets, which are defined in these papers here. So as usual, supersymmetry constrains a lot the structure of such effective field theory, and also of this string and membrane sector. And for instance, the tension of these objects, which is, generically dependent on the scalar fields, depends on the scalar fields in a way which is completely constrained by supersymmetry in terms, which is just given by supersymmetry, is fixed in terms of the bulk, the data specifying the bulk effective field theory sector. So even if supersymmetry provides such a strongly constrained effective field theory, it still leaves a large freedom from a purely four-dimensional viewpoint. And then a natural question to ask is, of course, at least in the swampland context, the natural question to ask in this context is, okay, if there is any general criterion which allows to characterize the inclusion of these objects into the landscape of effective field theories which admit a UV completion to string theory. So this kind of question is a typical question addressed in the swampland program. And we already heard about the swampland program in previous talks, and it will be reviewed by Irene in her talk in this workshop. In the following of this talk, we will encounter 4 of the main criteria, quantum gravity criteria, which are usually encountered in the swampland program, namely the completeness hypothesis, which claims that whenever you have a gauge symmetry, then the corresponding spectrum of charged objects is complete. The expected absence of global symmetries in quantum gravity theories, the weak gravity conjecture, which was also discussed in some detail by Eran in his talk yesterday, and the distance conjecture. Now, Now, so far I've been slightly more general, talking about strings and membranes, but from now on I will focus on strings, which indeed are the main topic of this most recent paper. And then the strings I have in mind are fundamental strings, that is strings which cannot be resolved into some smooth solitonic object within a four-dimensional effective description. And they are electrically charged under a set of two-form potentials. These two-form potentials are dual to a corresponding set of axions. And from this dual viewpoint, such strings can be regarded as axionic strings around which the axions undergo an integral shift. And these integers are just the charges, the electric charges of the string under the dual two-form potentials. Now, these axions are naturally completed by supersymmetry, and naturally complexified into some chiral scalars in terms of, they're complexified by some corresponding saxions and completed into full chiral multiplets, which are in turn dual to linear multiplets, which include, at the bosonic level, in addition to these two-form potentials, a set of dual saxions, which are a kind of Legendre form of this saxion here. Okay. Now here I just showed a few terms which appear in effective action, but one can write down the complete supersymmetric effective field theory. In particular, the string sector, the supersymmetry for the string sector, which is realized by imposing kappa symmetry, completely fixes the tension of the string, which appears here, in terms of the bulk scalars in this way. In particular, it has this nice linear dependence on these dual saxions. Okay, so one can write down a very general supergravities, including these strings. Now we can start looking at string models, or from an effective field theory viewpoint, invoking some swampland criteria. First of all, a priori, we could include or not include, just from a pure supergravity level, such strings into the effective theory. But actually, if we invoke the completeness hypothesis, actually such strings should be always taken in account once you have at least this description in terms of two-form potentials. Furthermore, once you have this description in terms of these two-form potentials, the dual description in terms of axions has an axial symmetry. So it's symmetric under continuous shifts of these axions. On the other hand, the presence of such a continuous shift symmetry is clearly in tension with the other quantum gravity criterion that I mentioned, namely the expected absence of global symmetries. And then, indeed, as it happens in string theory, such axionic shift symmetries are in fact at best realized at some perturbative level, in some perturbative regime, and broken by exponentially suppressed, in which they are broken by exponentially suppressed non-perturbative corrections. And then it's natural to, in order to really couple these strings to the effective field theory, we should restrict to some asymptotic regions around some infinite distance points, analogous to, oops, sorry, just a moment. No, scusi, sto facendo. Sorry for interruption. So analogous to the asymptotic regions considered by Thomas in his previous talk, but focusing on the asymptotic regions correspond around infinite distance boundaries, portion of the boundary which lie at infinite distance. Okay, so we need to focus on these asymptotic regions in which the corresponding axionic, the set of axionic symmetry we're interested in is preserved in the corresponding perturbative expansion, and only broken by exponentially suppressed non-perturbative correction. So we see that already at this level, these kind of strings, these fundamental strings, appear as natural probes of this asymptotic region of the field space characterizing a given effective field theory. So if you want to have in mind a concrete set of models, you can think of, for instance, the set of heterotic of models obtained by compactifying heterotic string theory on a Calabi-Yau threefold, and consider the asymptotic regime corresponding to a large volume regime. The corresponding Kähler fields are the usual complexified Kähler moduli. Indeed, in this regime, the theory is invariant under continuous shifts of these axions, which are nothing but the Wilson lines of the B field, at the perturbative level, while this shift symmetry is broken by exponentially suppressed Walsh instantaneous corrections. Now, another important point is the fact that strings and also membranes in 4 dimensions have a strong back reaction, which cannot be neglected. So, in particular, this back reaction destroys generically the asymptotics of a given underlying configuration and forces the underlying scalar fields to flow. So this in particular means that we cannot treat such things at the probe level, neither we can consider them as kind of states defined excitation of a given vacuum state. Nevertheless, they admit a perfectly sensible interpretation in terms of contribution to the effective field theory. And actually, from this EFT viewpoint, the brain back reaction, their back reaction, can be interpreted as a corresponding, as an RG flow of the corresponding string couplings. So for instance, the flow induced on the scalar sector corresponds to, provides, implies a corresponding running of the tension of the string, which is more precisely defined at the cutoff scale characterizing effective field theory. Okay, and then as you change this cutoff scale, this change of the profile of the surrounding scalars will induce a corresponding change in the tension of the string. And now, because of this strong back reaction, which cannot be neglected, it's natural to focus on the strings which naturally drive, which automatically drive the surrounding scalars towards the weakly coupled region, in which, as I said, we can couple such objects to the effective field theory. Okay, so we will, so such strings admit very naturally an EFT description. Basically, we're interested, we want to define the effective field theory at some cutoff scale. So we are interested in the behavior of the fields as they approach the string, particularly at the cutoff length scale at which we are defining our effective field theory. And so we need the theory is weakly coupled very close to the string at this minimal cutoff scale. Okay, so these kinds of strings, characterized by such a back reaction, admit naturally, as I try to explain, coupling, controlled, weakly coupled description within effective field theory, and for this reason, we dub such strings EFT strings. On the other hand, other strings will lead, the flow induced by other strings will lead, will drive the scalars towards some strongly coupled region. Now, this identification of these EFT strings is very qualitative. So in order to make it more quantitative, we can use supersymmetry. Indeed, as I said, we are interested in the behavior of the scalar fields around the string, very close to the string. So in a semi-classical regime, we can consider the string very close to the string. The string can be approximated to a straight one. And then locally, the string, such a straight string, preserves 1/2 of the 4 bulk supersymmetries, and also the corresponding back reaction can be well described by some BPS string flows, which have been studied in the past, in particular in these 2 papers. For this talk, it is important to realize that, in particular, if we focus on the saxionic sector, on the flow of the saxions which are present, which characterize a given perturbative regime, then this saxion will flow as we approach the string in the radial direction towards straight lines in the plane corresponding, to the saxionic plane. Okay. Furthermore, if we if we use this logarithmic parameterization of radial direction, which goes to +infinity, this sigma here defined this way goes to +infinity as r goes to 0, then these straight lines are actually linear. This saxion will change linearly with this parameter sigma, and the coefficients are just given by this. Here I'm using an index-free notation. So these are just this is just a charge vector whose components are the charges of the string which is generating the flow. Okay, so by supersymmetry we can have a very precise description of the flow or the back reaction induced by such strings close to them, and then we can combine this observation with expectation that in supersymmetric models, in such perturbative regimes, the non-perturbative breaking of axionic symmetries is dominated by BPS instantons. And then by using this observation, we can characterize the set of possible EFT string charges as those charges which have a non-negative pairing with all the charges characterizing all the charges of these BPS instantons. Okay, why? Because for such BPS instantons, the contribution to the effective field theory, the contribution of such instantons to the effective field theory, contains this typical exponential dependence on these scalar fields, in particular on the saxions. And then if you satisfy this condition, then the corresponding the flow activated by a string with such a charge will preserve the exponential suppression of the correction along the flow, while non-EFT string will activate a flow which will make such a correction explode at some point, hence destroying the perturbative regime. So far I've been quite general, so let me provide a more concrete model. Let me describe a more concrete model, trying to clarify the ideas. Again, one of the simplest but still non-trivial examples can be obtained by considering again a heterotic compactification of a Calabi-Yau. Now take a specific Calabi-Yau threefold obtained by considering this an elliptic fibration of a T2 over a base which is just a P2, a complex two-dimensional projective space. Okay, such a model has 2 Kähler moduli, and let's focus, as already mentioned, on the perturbative regime corresponding to a large volume, in which these 2 Kähler moduli, these 2 saxions, are very large. Okay, these 2 saxions measure basically the volume of these 2 cycles here. Now, as I said, so here we can see a concrete realization of the general expectation that the corresponding perturbative axionic symmetries are broken by a set of instantons, or a set of BPS instantons, which can indeed be identified with fundamental strings wrapping such effective divisors. So the full set of instanton charges, of BPS instanton charges, denoted by the symbol, can be identified with a cone of effective curves. In other words, the modicon of the internal space. Instead, by looking at the dual set of string charges, we can first discuss the set of possible BPS strings, which can be obtained associated with this perturbative regime, which correspond microscopical to NS5 branes wrapping effective divisors. So the full set of BPS string charges can be identified with the cone generated by effective divisors. And this discretized cone, this plot here, is the union of these two colored regions, and is generated by these, and is generated by these two vectors, this one and this one, which correspond to this divisor, and which is basically the push forward or the base under the global section of the elliptic fibration, and this divisor, which is basically a vertical divisor over the P1 in the base. Okay. The point is that not all of these strings correspond to EFT strings. You can see this either by computing the pairing with the dual BPS instantons, and the pairing in this case boils down to the intersection number, corresponds to the intersection number between divisors and curves, or more directly by following the corresponding flows in the axionic space. So take, for instance, this divisor here, which corresponds to this vector here, and then, as I said, the corresponding axionic flow will be given by a straight line generated by this vector. So if you start, for instance, from this point inside this axionic cone, which is nothing but the Keller cone of this Keller cone here of this space, then at some point, actually at finite distance, you will reach the boundary, the finite distance boundary of this Keller cone, and in this region, the perturbative approximation breaks down, Washed instanton correction should be taken into account. Okay. On the other hand, so this is true for all these charges here in this gray region. Instead, the EFT string charges, the ones which have a nice weakly coupled, admitted this nice weakly coupled incorporation into effective field theory, correspond to this set of charges and can be obtained basically by discretizing this axionic cone. Okay, and microscopically they correspond to NS5 branes. I mean, the corresponding strings are given by NS5 branes wrapping a so-called set of NEF by wrapping a so-called NEF divisor. Okay, so this set of EFT string charges can be identified with the cone of NEF divisors. Okay.
Okay, you have 5 minutes.
5 minutes only. Okay. Okay. So this example already contains some key ingredients which we found to be quite universally present when we try to study these asymptotic regimes, namely the fact that such asymptotic regimes can be identified with a given axionic cone whose deep inside correspond to the perturbative region, the truly perturbative region. This axionic cone corresponds in turn to a set of EFT string charges, which are basically obtained by discretizing this cone, or better, the closure of this cone. And the dual BPS instantons are obtained by discretizing the cone dual to this axionic cone. Okay, so we tested this description, this characterization of these perturbative regions in many examples, heterotic type 2A, type 2B, F theory, M theory, and it seems to work in all cases. In particular, notice that the set of EFT string changes can be regarded as generating this axonic cone. And this observation can be rephrased somehow in more physical terms in terms of a new Swampland criterion that we proposed, this distant axonic string conjecture, which basically claims that any point at infinite distance in field space can be reached by following an EFT string flow. So it can be identified as the endpoint of an EFT string flow. So this is one of our main bottom lines. Another interesting observation is that in all the models that we could consider studying in detail in string element theory, the tension and the physical charge of the string satisfy this kind of this bound, which is of the same kind that appear in the formulation of the weak gravity conjecture. And if we assume the validity of such a bound, together and combine this bound with this, with our conjecture, which claims that any point at infinite distance can be reached by an EFT string flow, then we reach an interesting result, namely by just using supersymmetry and combining supersymmetry and this bound, we can relate the distance traveled along an EFT string flow to the change, the corresponding change of the EFT, or the tension of the EFT string, which is generating the flow. And then turning this inequality around, we can write this inequality, which is basically telling us that the tension of the string, the EFT string, which is generating the flow, decreases exponentially with the distance as we move along its own flow, which can be interpreted, I mean, this change can be interpreted indeed as an energy flow, as I explained at the beginning. So at some point, this tension will become too low, lower than the cutoff scale of the EFT, and then in principle, I mean, the semi-classical description breaks down. In principle, you should include all quantum excitation of the string, and you get a kind of purely EFT realization of the breaking that is, let's say, part of the distance conjecture, okay? Now, on the other hand, the distance conjecture, I mean, in principle, there could be additional microscopic degrees of freedom, which may contribute to the breaking of the EFT, and which then can contribute to the realization of the distance conjecture. And they could come from the microscopic completion of our effective field theory, and indeed they are generically present. For instance, they correspond to some Kaluza-Klein modes. Now, let's call M star the corresponding mass scale, the lowest mass scale corresponding to this UV degrees of freedom. And in general, there could be, I mean, such UV degrees of freedom with an M star, which also exponentially goes to 0 as we move along these EFT string flows. Now, a priori, our effective field theory knows nothing about this M star and the corresponding UV information, okay? On the other hand, by going through a lot of examples, we found a quite intriguing relation between such an M star and the tension of the string, which is the EFT string, which is generating the flow to infinite distance. Namely, this M star squared scales like an integral power of this tension in Planck units. So we promoted this observation to a second new swampland conjecture, which, if true, would really provide some non-trivial information on the UV completion of the theory from purely EFT ingredients. Okay, so we didn't have identified a way to fix the scaling weight, this integer here, from purely EFT arguments, but I can say that we observed that in all the models that we consider, string and theory models, the only allowed values, which appeared are 1, 2, or 3, no higher scaling weights. Finally, let me mention that in the case in which the scaling weight is equal to 1, actually, you see this m star squared is of the same order of the tension of the string, and then actually the EFT string modes compete with this microscopic tower of states which come from the UV completion of the theory, as it happens in the emergent string conjecture proposed by Lee, Leche, and Weigand. And actually, they also propose that in such cases, there exists a dual formulation of this limit, of this of the full setting of the model, in which such string should be identified with a fundamental string. So how much? I think that I run out of time, right? I don't know. Okay, so I can conclude with this slide and thank you.
Thank you. Thank you, Luca. Questions? Any questions from the audience? Okay, don't try us here. Okay, if there are no questions, let's thank Luca again.
Okay, thank you.
And the next speaker is Nicolo Petri. He's going to talk about bubbles of nothing and ADS instabilities.
Hi, can you hear me?
Yeah, now you.
Okay, perfect. Right. So first of all, I would like to say thank you very much to the organizers for giving me the opportunity to be here today, at least unfortunately online.
Can you speak louder?
Yeah. I'm gonna to share my screen. Just a second. Can you all see my screen?
Yes, but can you speak a little bit louder? Because we cannot hear you too much.
Okay, I have to, okay. Maybe in this way is better.
Yeah, that's better, yeah.
Is better, okay. All right, so my talk is based on this paper published with Giuseppe Di Vitetto from Padova University and Marjo Ischillo from Uppsala University at the beginning of 2020, and on some unpublished results that we are going to put on the archive, I hope in the next few days or late weeks, with Peter Bowmans, Davide Cassani, and again, Giuseppe from Padua University. So let's start with some words of introductions and motivation. I hope I will not repeat again things that have been already told, but just to remind and give the beginning of my talk. So we have a very important and crucial challenge, that is one to provide and construct an interpretation in string theory, in a UV completed theory of gravity, of those solutions of those classical solutions involving the gravitational field without any supersymmetries. So of course, the presence of supersymmetries is a sufficient condition for the stabilities of gravitational system, but all we know that in some way we need to understand how it works, the dynamical SUSY breaking, in order to build up some models with the aim to be realistic from the point of view of phenomenology. So even if we saw a huge effort in the literature in the last 25, 30 years of people trying to do exactly these things, so try to construct vacua or solution in lower dimensional gravity theory and try to interpret them in terms of non-perturbative objects coming from string theory, we saw in last years that Swampland conjectures radically questions the presence of these systems in the so-called landscape. So among the various conjectures, I would like to mention the first one, and maybe the most important one, the weak gravity conjectures, whose admit, among various implications, the fact that those ADS vacua without supersymmetry should in principle decay once they are embedded in the full UV completed theory. So my talk follow a little bit this general direction, and I will focus on that behavior that anytime we try to embed this non-supersymmetric vacua solution in higher dimension we encounter. And I'm talking about instabilities. So to my point of view, in principle, instabilities are not something bad in principle, but should be a peculiarity that we should study in order to understand how we can effectively describe the Sitter space-time, for example, or non-supersymmetric holography. So first of all, I have as a big aim that one to try to test in some concrete setup the Swampland conjecture, and secondly, try to understand more generally if is it possible to provide in string theory to construct some kind of interpretation of this non-supersymmetric vacua. So in my talk, I will mainly focus on these particular non-perturbative instabilities describing sometimes the gravitational field that have been discovered by Witten in 1982, studying the 5-dimensional Kaluza-Klein vacuum. I'm talking about bubbles of nothing. So first of all, I will try to, in a very quick and superficial maybe way, I will try to introduce these instabilities and say something about them. And then I will try to push a bit the analysis by Witten to a slightly more general case. So I will consider any general relativity in the dimensions, and I will include a negative cosmological constant in this context. And then we will try to see if we can say something regarding the existence of these bubbles, even in the case of ADS within simple general relativity models. And then finally, I will present some work in progress in which we will try to see what we can say when we go further in our analysis and we try to include some scalar field in a model and consider a concrete compactification coming from string theory. So we know there are many, many examples of non-supersymmetric ADS vacua that we encounter in perfectly working compactification, consistent truncation. So we will see, we will study a very concrete example that is an ADS4 example, a vacua worked out in massive 2A with an internal space given by a 6-sphere, and we will see what we can say on stability or instability. So just for having a quick remind, so we have the need to understand the stability, the non-perturbative, the quantum instability of space-times, and usually the semi-classical approximation is the most doable, the easiest approach. And this is exactly what Witten did at the beginning of 80s when he studied the stability of the KK vacuum in 5 dimensions. So when we deal with gravity, we cannot proceed by comparing the various space-time with different boundary conditions, but same energy, because energy, when gravity is included in the game, is of course something depending strictly on the boundary condition of the space-time. So the idea was to study instantons present in the KK vacuum by starting from non-extremal black hole. So basically, we start from a Schwarzschild black hole in 5 dimensions, and then we pass to the Euclidean space, analytically continuing the time in this new phi coordinate. And then, as usual, when we pass to the Euclidean, we obtain a Euclidean background, and this Euclidean background is completely smooth once we excluded the part corresponding to the interior of the black hole, and we topologically included the border by doing this periodic identification on the Euclidean time. So in this way, we produce a completely smooth solution in this interval, and a solution that asymptotically reproduces the putative vacuum we are considering, the KK vacuum. So with a very intuitive calculation, what we then did has been to derive the Euclidean action for this particular background, and it showed that it's basically finite. So these three properties, smoothness and to reproduce the putative vacuum at infinity and a finite Euclidean action, are enough to guarantee us the fact that within the KK vacuum an instanton is present. So now, who is this instanton? Well, in order to understand which is the geometry describing the instability of the KK vacuum, we have to come back to the Lorentzian. So in order to do that, we analytically continue this solution within the free sphere. And doing that, what we obtain is basically a three-dimensional de Sitter slicing. So this is a crucial feature of any time we need in gravity to implement some time-dependent behavior, like an instability, in some way, de Sitter comes up. And this is exactly the situation. So what we obtain is basically a background, a geometry in 5 dimensions, in which there is a probability, a quantum probability, that in a given point and in a given time, a bubble appears. And the geometry of the surface of this bubble is actually described by this de Sitter geometry. So the K property of this bubble, that expanding in an accelerated way, is that one to be geodesically complete in the exterior. So that means that we cannot push an observer to cross the wall of the bubble. And in some sense, this is the reason why we can call it bubble of nothing, because there is no inside. We cannot define neither an observer within there. So we have this bubble expanding and actually destroying the KK vacuum without substituting it with any kind of true vacuum or something like that. And the last crucial property I wanted to include is topological. And it consists on the fact that while the bubble is expanding, there is the KK circle that is gradually shrinking in a smooth way. So this is the K property allowing actually this very particular decay. And this is the K property that we are going to use to extend this particular geometry, this particular instability, to the case of the cosmological constant. So now we started from 5 dimensions. Now we can pass to D dimensions, D plus 1 dimensions, and include this negative cosmological constant. So in comparing it to strain compactification, this is a very simple model. And we need, as I told you, a circle in order to build up such a geometries. And the best way to do that is to write down this D plus 1 dimensional space-time using the KK reduction ansatz. So in this way, we can pass to D dimensions and work out some de Sitter geometries that actually produce all the properties we need, that basically I told you before in the 5-dimensional case, to reproduce a bubble of nothing. So which is the difference with respect to the previous case? Well, the main difference is the fact that when we send the coordinate rho to infinity, actually we are going to reproduce ADS in a very particular foliation in terms of the Sitter foliation, but actually this is ADS. So in some sense, we had been able to prove that this class of D+1 dimensional geometry actually reproduce all the properties we need to represent well-behaving instantons within ADS vacua in these models. And in this sense, we could say that they represent actually a sort of an extension of their original result. So now, obviously, the aim would be that one to apply the same approach to already known non-supersymmetric ADS vacua, not in simple general relativity plus a cosmological constant, but in a consistent string compactification. So now the problems here are of the two order. The first is technical. So when we deal with a string compactification, including ADS, actually we have many scalars that play together to form a scalar potential. And the extreme of this scalar potential reproduce the vacuum of the theory, the cosmological constant. So this, the presence of this scalar potential and of this scalar field actually complicate incredibly the field equations. And then there is a second problem that is physical. So when we are dealing with 10-dimensional solution, even if we are in supergravity, even if we are giving a classical interpretation of things, we are still claiming the fact that behind there is a quantum theory. And for example, when we have a divergent behavior, behind that divergence, there is an object. So the problem at this point is to provide an interpretation of these bubble geometries, for example, in terms of branes, in terms of objects of a quantum theory. And this is something that is actually much more complicated than the simple technical problem of solving the field equations. So in this general context, what we did has been to choose a very interesting example. So let's consider massive type 2A string theory and supergravity. So some years ago, a very relevant and interesting consistent truncation of this theory has been worked out around the 6th sphere. So this consistent truncation reproduces a gauge supergravity in 4 dimensions. That is the so-called ISO 7 gauge supergravity. So this theory, within this theory, a consistent number of various ADS vacua and more complicated solutions have been worked out in the last years. And in particular, there is an example that is an ADS4 vacuum with a 6th sphere as an internal space, of course, and a G2 residual symmetry, that it is very mysterious because basically it passed many tests. So it is a fully non-supersymmetric vacuum that has been shown to be perturbatively stable within the context of the truncation in the ISO 7 supergravity. It has been shown to be classically stable also at the level of the full KK modes of massive 2A on a 6th sphere. And then there are also examples in which it has been shown that this vacuum is also protected against some brane jet instabilities that are non-perturbative examples of instabilities. So this example is of particular interest because in some sense it poses a challenge to swampland conjectures. And our idea to study this interesting situation moves from the idea consisting in say that gauge supergravities are not always good effective field theory. So anytime we pass from quantum to classical, or every time we truncate a theory from higher dimension to lower dimensions, we lose informations. So actually a consistent truncation identifies only a particular sector of the quantum theory, and the risk is that one to lose some effects that could be crucial. So the idea the things that we try to do is to come back to 10 dimensions and search for some de Sitter backgrounds that more or less was having the same properties of the de Sitter backgrounds of the bubble of nothing that we study in general relativity. So in particular, we search for de Sitter, three-dimensional de Sitter slide solution that reproduce in the asymptotic our ADS4 vacuum. And what we did has been, of course, a numerical integration, because the equations of motions of this particular background, and I wrote only the metric and not the fluxes, are very complicated. So what we actually found is a very complicated curve, a numerical curve, in which we identified three different phases, three different regimes. Actually, there is the first regime that is the regime that we use to make start the integration. That is the IR, let's say, and it consists exactly of our ADS4 vacuum. Then at the end, in the UV, what we saw, it is a divergence. In particular, it is a divergence dressed by a D2 source. So what we saw in the UV is that our geometry of characterized by de Sitter slicing reproduce a D2 geometry. And of course, I'm talking about instantonic D2s. So D2s that fill the de Sitter geometry in here. And the crucial property of these D2 branes is that of to be not completely localized within this 10-dimensional background. So in particular, these D2 branes that our solution reproduce in the UV are D2 branes whose charge is mirrored over the direction of this sixth sphere. And this property is crucial to understanding why in 4 dimensions was not possible to find this instability, because the consistent truncation to ISO 7 supergravity only capture localized D2 sources, not smeared. So given this intuition, what we saw is that there is an intermediate phase within interpolating within the ADS vacuum and the D2 sources. And this intermediate phase is a completely discharged, it is described by a completely discharged geometry, characterized by a dilaton that shrinks smoothly over the source, while the radial flow of the solution reach the D2 brane, our dilaton shrinks smoothly to 0. So just to give you an idea of our unpublished results, the first 3 plots represents the work factors of the matrix U and W, and the third is the dilaton. So we have the orange line and the green line representing respectively the ADS4 vacuum and the smear D2. And as we see that in all 3 plots, we see how the 2 extremum behavior, the IR and the UV, the curve match perfectly. But then there is this intermediate behavior with the blue one, that is our full solution, that is something different with respect to the 2 situations. So in order to understand which is the main difference, it is better to look at this plot. So in this plot, we basically represented the so-called effective potential, that is basically a function obtained by taking all our 10D backgrounds, evaluating the action of supergravity in 10 dimensions over this background, and then plugging the numerical flow. So in this way, actually what you obtain is, okay, some terms that are corresponding to kinetic terms of various fields, U, W, phi, and so on. And then other terms that represent actually some potential terms. And typically these terms depend on Roma's mass, on the curvature of the Sitter or of the sixth sphere, on the fluxes. So in particular, if we go close the origin, this is the UV. We see that there is a curve, the blue one corresponding to the sixth flux, that explodes while all the others die. And this is exactly the point in which we have the D2 source. So on the other side, we have that's the contribution of the curvature of the sixth sphere, and also that one of Roman's mass, but it can be seen here because it's very small, but it can be zoomed and it can be seen that Roman's mass take a more important value at infinity here, becomes important. And this regime is that one corresponding to ADS. And then we see there is an intermediate regime in which all the fluxes are unimportant, are subleading with respect to the contribution associated with the green line, that is the curvature of the sitter. So this is the regime that we call bubble regime that corresponds to a discharge solution, a discharge regime in which our geometry represents a three-dimensional de Sitter foliation with a shrinking dilaton. So why we call it bubble regime?
You have 5 minutes.
Okay. Well, as I mentioned before, what we are trying to do is, okay, we worked out a numerical solution. Now we try to take various approximate solutions and glue them in a dynamical way, of course, in order to understand the various regime, the various pieces of the radial flow of this numerical solution that we obtain. So we have the two regimes approximated perfectly by the ADS4 vacuum and the D2 source. And then we have this solution, this regime, that we can approximate again with some discharge solution with the Sitter foliation and the dilaton shrinking. So who is this solution? Well, if one imagine to reduce this numerical flow in 4 dimensions, of course, not in the ISO 7, in a more general truncation, we will see that we are basically describing a 4-dimensional domain wall characterized by the Sitter foliation and with a dilaton shrinking. And while with this dilaton is shrinking, the radii of the Sitter and of the sphere remain finite. And this property, actually, it is more or less equivalent to define the presence of a bubble. There is, just to conclude my talk, another way, maybe more intuitive and suggestive to understand the physics of this bubble regime. I told you, by looking at this graph, it is clear that all the fluxes in here are unimportant at the level of the dynamic of the solution with respect to the contribution of the geometry of the Sitter. That means that if we are looking for that particular regime and we wanted to provide an approximate solution to match the curve, we can pass to massless 2A and then to M theory, because actually what we are doing is only to try to find an approximate solution and see if we can glue it with the other regimes. And this is actually what we did. And the very interesting thing is that we can reverse this argument by starting from M theory and take, in analogy with Witten, a 5-dimensional Schwarzschild black hole cross a 6-sphere that rests there like a spectator, and then make the double analytic continuation within there, as I explained you, in order to produce a bubble of nothing, and then reduce to the circle of the bubble of nothing in 11 dimensions. And actually what we find is a discharge solution in 10 dimensions with a dilaton shrinking, and the dilaton is exactly the quantity that is associated with the circle in 11D. So what we showed is that this particular massless 2A background coming from Schwarzschild in 11D is the unique one that we can use to match in massive 2A the ADS4 regime with the D2 source on the other side. And for this reason, actually, we call this particular intermediate regime the bubble sector of our vacuum. So just to summarize and conclude, we started just introducing in a very short way the idea of Witten of bubble of nothing in 5 dimensions. concerning the KK vacuum, and then we extend this bubble of nothing to the case of generic D+1 dimensional gravity model with a cosmological constant. And what we see is that at this level, there is always a quantum probability for the ADS vacuum to decay into bubble of nothing, into generalized, let's say, bubble of nothing. And then at the end of the story, I try to use this insight in a context of a strain compactification in which there is this ADS4 vacuum in massive 2A that seems to work very well, but with a more careful study of the property of the 10-dimensional background, it seems to manifestate some interesting behavior. But we will see. Everything is still under research. Thank you very much for the attention.
Response.
Yes. Hi, Nicolo.
Hi.
Thanks. Nice talk. I was wondering if you think that in this ADS 4 times 6 case, the studying bubbles of nothing is the most promising decay channel for a possible instability, or if you think there may be other decay channels with higher decay rates, or even just simpler to study.
Actually, I don't know how to reply to your question because it is very hard to understand. It has been very hard to understand to see the existence of this decay channel, and yeah, so I don't know. This is one.
So you would say that it's confirmed, like there are bubbles of nothing in this geometry. Or is it still?
Well, it is call them bubble. I didn't call them bubble of nothing. I said that I took inspiration by the pure bubble of nothing analysis in general relativity, because in this situation there is a source, and this source typically make more complicated the study of the Euclidean action. So there is a source, a brane source that feels that rests a 6 flux, and this 6 flux fills the vacuum. So it manifests some properties of the Ooguri-Buffer decays. And at the other side, it manifests some properties of bubble of nothing decay.
I see. Thank you very much. I'll wait for the paper.
Yeah,
thanks.
The question by Carlos Núñez. You can unmute yourself.
Hello, Nicolo. Can you hear me?
Yes. Hi.
Hello. How are you? A couple of questions. Very interesting, all this story. Is it correct to think that this corresponds in some dual perspective to a field theory on the sitter? So in the particular case, you discuss a field theory on the sitter 3?
I cannot reply you in a very with a solid. I don't know. There is an interesting paper on these aspects of bubble of nothing called "The Dual of Nothing" of 2004 by exactly. Yes, one should analyze more deeply, to my opinion, the global properties of the ADS vacuum when you write it in terms of the sitter foliation.
Yeah.
That for holography, it turns out to be non-trivial.
Right. And another, a bit perhaps technical, is when you talk about the D2 source in all this, is what you're saying is that the exterior derivative D of F6 is either a delta or the volume of the 6th sphere. How you see that there are D2 sources smeared?
Well, you see that there are D2 sources. Otherwise, you you wouldn't conserve the charge within the bulk.
Mm-hmm.
Because otherwise you would get basically, so you can take the geometry of the solution, no? So you have a 7-dimensional internal manifold here.
Yeah.
Right. So if you don't have a source, so a point localized within this 7-dimensional manifold, you basically obtain that the integral over this 7D manifold of the df6 is 0.
I see. Okay. So, okay.
And this means that, yeah, you need to...
This would probably translate into df6 equals to something different from 0.
Exactly, because otherwise you would obtain, using the Stokes theorem, that the 6 flux is 0.
Okay, exactly. Yeah. This direction R is non-compact. Is that correct?
Yes, of course.
Good. Perfect. Thanks very much.
Thanks.
Other question? Yes. Okay, if there are no other questions, let's thank Nicolo again.
Thanks.
And all the speakers of this afternoon, and we close the session. See you tomorrow. Bye.